Yeah. All right. Hi, everyone. Hello. So we're back. Discord. Hi, Discord. Can you hear me? Okay. Okay. All right. Welcome back from the break. And welcome back from the midterm experience. Because of what happened, we had to basically take the max, as you remember, between the last questions. As a result, the average in the midterm was, partly as a result of that, and partly as a result of your studying really well, I suppose, the average in the midterm was quite high, so low to mid 80s. And you know, that's great. So we're not going to make any adjustments or anything like that. Usually it's the case in this course that the average at the end of the day is high 70s. I suppose so. Of course, kind of view of the policy is that you get what you get. Like if you perform well, if the class performs well, then they should get a high grade. Now, usually the average on the exam is lower than the average on midterm, so I don't expect anything out of the ordinary for this class. I would say that if you want to get kind of, you know, an estimate for how well you do on the exam, of course, if you study more, you'll get more. If you study less, you'll get less. But if you look at the overall grade on the midterm without taking the weird max, that might be kind of a better estimate of what to expect on the exam if you continue studying at the same rate and with the same effort as you're doing now. Of course, there's always room for improvement. And if everyone does great, then so much the better. So what we'll do for basically the rest of the semester is, rather than focus on the basic tools of Python, which we basically already have, we're going to focus more on making programs more efficient and focus on problem solving. So solving problems that might not be that trivial to solve. And sometimes, as you'll see, a combination of both. So just as a preview of the kind of thing that I'm talking about, this is, by the way, in the notes as well. So we'll be talking today first about kind of a simple function. So just finding the index of the element E. And I think kind of you know how to do this. Hopefully by the end of the lecture, or certainly by the end of Wednesday, you'll also see situations where it's possible to solve this problem much more efficiently than you would get using a naive method. So to step back a bit and kind of wax philosophical for a bit, we currently have basically all the tools that are needed to solve any problem that's solvable with a physical computer, right? So loops plus functions, that gets you anything if you combine them in an interesting enough way. So according to what's called the Turing thesis, so this is not on the exam, this is just like a diversion for a couple of minutes. So I'll put it in the modern way rather than the way that Alan Turing put it. So anything that you can do with loops in Python, you can do on any computer and vice versa, right? So the idea here is if you have a computational problem and there is in principle a solution to it that uses kind of the kind of hardware that we have, then just loops is enough. So Turing thought about it during, the 1930s, 1940s. Turing, in fact, was one of the first people to build an actual physical computer. But when he was thinking about this, he actually made a theoretical computer that wasn't implemented, that was called a Turing machine. And the original Turing thesis was that if you can do something on a Turing machine, which was a theoretical computer, then that's equivalent to anything that you can physically implement. So that, of course, has kind of interesting philosophical implications if you think that you are yourself kind of a computer, right? So if you think that your brain, has receptors and those receptors activate neurons when, for example, the light hits your retina, and then those neurons activate other neurons in your brain. And eventually, through this kind of weird process, you'll look and say, oh, that's the Young size, right? If you think that, then according to Turing's thesis, well, you can in principle implement any kind of thought process or, a subconscious thought as well that goes on in your brain just using loops. There are kind of various objections to that. So some people just reject the whole idea that that the human mind is a purely physical process. Some people, that's not kind of a common thing, but some people think that because of kind of weird quantum effects that are going on, it's actually not the case that what the brain does is implementable using loops. There are kind of serious people who think that. It's not kind of really nailed down how exactly that goes on, but that's something that people think. And of course, up until very recently, it was the case that you would say, well, very clearly a computer is not like a human. It can't do anything that's near, for example, being able to produce speech or produce code. With ChatGPT, that argument has gotten maybe weaker. Of course, ChatGPT is still not great, although it is pretty good at solving ESC 180 midterms if you try it. It's pretty good. So in fact, last year, I gave the ESC 180 exam to ChatGPT, and it got a 95. So it couldn't solve two of the problems. And then in February, an update came out, and it solved one more. And then GPT-4 came out last spring, and currently GPT-4 solves the entirety of last year's ESC 180 exam perfectly. It still struggles a little bit with ESC 190, so there is some competitive edge there for you to look at. So, okay. So that was a diversion. I'll take one more minute to mention the extended Church-Turing thesis, which says that anything that you can do with loops in Python efficiently, you can do on any computer efficiently, and vice versa. And here, again, kind of what we mean by efficiency, you'll know more about it by the end of the lecture. The basic idea is, well, if you think about just loops in Python, well, loops do one thing at a time. Brains do not, right? So there's multiple processes going on in the brain. In fact, kind of tens of thousands of processes. So you might say, well, because of that, brains can do stuff much more efficiently than, for example, computers. And there is probably some truth to that. Now, GPUs, graphical processing units, also can do multiple things at a time, as can modern CPUs. There is another aspect to it, which is in some sense, you could say, well, like, what if you use quantum effects? It might be, although that's not proven, that a quantum computer can be more efficient than just what you can do on a laptop with just loops. So to be clear, a quantum computer is a device that uses quantum mechanics in a substantive way in order to do computation. Of course, any modern computer would not work without quantum mechanics, in the sense that the transistors would not work if quantum mechanics wasn't true. But that's not the same thing. So a loop in Python, you don't need like in a world without quantum mechanics, you can still have loops in Python, right? So you can build just like a mechanical device, like we saw, where like it's just gears and it would still work. Anyway, so that was a little bit philosophical, and maybe took a little bit more time than expected. But let's go back to analyzing how fast we can do this kind of thing. So, of course, you can just say return E and L and be done with that. It would be difficult to analyze what exactly happens here because that's internal to Python. So what I'm going to do instead is I'm going to write out the process that Python, as it happens, I know that that's what it does. You can look up what it does in ESC 190. We'll see implementations of Python and C where you can check that that's exactly what it does. And what it does is, well, it does a loop, right? So what's going to happen is we're going to say, sorry, so I said the index, of course, so L.index. So what we can do is we can say, okay, so for I in range length of L, if L at I is equal to E, we return I. So let's just assume that the element is an L. All right. So now I want to know, okay, how efficient is that? And here, like, you can ask the question, but you start thinking about it and you see that you need to actually define your terms. Like, what does it mean? How efficient is it? Well, sometimes it runs fast, sometimes not as fast, depending on how long L is, whatever, and also how lucky you get. If L at 0 is equal to E, then you return right away. So we need to do something here to define our terms. So here's a first stab at it. So I can say, okay, so in seconds for a list L of length L, if we don't get lucky with L at I equals to E for small I, how long will the function take? So that's kind of the first try. So the problem is, so that's clearer, right? So it says, okay, well, like, forget the case where L at 0 is equal to E and you return right away. But here, say, what, don't get lucky. So what do we mean? So what I'll say is, okay, if we get as unlucky as possible, meaning that E is at the very end, how long will it take? So I'll rewrite it. So I'll just copy and paste it and rewrite it with, instead of if we don't get lucky, I'll say in the worst case, how long will the function take? So that is still a problematic thing because, of course, if you're only ever planning to run this code on my laptop, then, well, you can measure it. But, you know, you buy a better laptop and it's going to be faster, right? So if we want to know, okay, like, how efficient is this function in principle as opposed to on a particular device, which sometimes you might like to know, right? So like, you're building a particular chip that you're going to use in some kind of device. Well, yeah, like you want to know in seconds for a plausible input size, how long is it going to take? But if you're just looking at the function abstractly and saying, well, how efficient is it? Maybe you're writing it down on an exam or something where you can't even run it on a computer. You want something better. So what we can do is kind of going back to thinking, okay, we have loops and maybe we're even running it on like a mechanical computer without transistors. We still want to know how efficient is that going to be. And what we can say is instead of in seconds, we can say in operations. So what I mean by operations is something like that. So like some kind of elementary transformation of the data in the computer. Right? So the way I imagine it is, well, if I'm running this, well, I is going to be 0, and then I need I is going to be 1. Well, in order to switch from 0 to 1, I need to add 1 to I. And also, I need to say, oh, I need to go to the memory table and find L at I. And then I say, well, like once I found L at I want to compare it to E. That's another thing. And then I'm going to say, well, like once I know that this is false, I want to switch to the next line. If I know it's true, I want to switch to a different line. Every one of those things is some kind of transformation. You can even spell it correctly. Elementary. So it's some kind of transformation of what the data used to be. Right? So specifically, let's do an example. Let's say that L is like 5 to 10, and then we are unlucky, so E is 10. So what happens on the computer approximately if I say find I, L, E? Well, the first thing that happens is L gets sent to here, and E gets sent to here. Right? So L is set and E is set. And I'll count it as 2 operations. So 1 to set L and 1 to set E. And now I'm going to say, okay, so for I in range length of L, so we need to find length of L, and we need to put it somewhere. So range is actually a complicated construct which takes more than 2 operations, but that's something that you need to set up. Like if you're using range, you need to set it up. So that is again 2. And here I'll start making things up, and you'll see that in this kind of analysis, you make things up all the time. So let's say K operations. So what I'm doing now is I'm saying, okay, so set I to 0, and then set I to 1, and then set I to 2. That is 3 operations, plus 1, plus 1. Figure out if we're done. 3 times that we do it, 3 operations, or something like that. Comparing L at I to E. So that's 1 for accessing L at I, and then 1 for comparing L at I to E. So 2 operations. And then return I, well, that just happens the once. That's just because it only happens once. The other times you just don't do it. So this is all a little bit nebulous, right? So you can very easily say, well, like length of L, like how do you do that? Well, you need to go to the memory table. In the memory table, it happens that the length is stored somewhere. We don't exactly know how. In fact, the Python standard doesn't specify how, depending on how it's stored exactly in the memory table, it might take longer or shorter. And then range is a complicated thing, which we don't exactly know to translate in the same way that we translated L.index to this kind of thing. So we don't exactly know K. But the point is that none of that actually matters. The reason none of that actually matters is that we don't know how long an operation takes anyways. So what we can say, though, is that we're taking approximately length of L times whatever this is operations, right? So this is 1. So this is setting I to 0, 1, 2, and this is times 3 because 3 is length of L. And then this is 1. So this is in fact 2 times 3. So this is 2 plus C, right? So what I've done here is I said, okay, like anything that we repeated 3 times here, in general, we'd repeat length of L times. The count here is always going to be a little bit weird because you make arbitrary decisions, slightly arbitrary decisions about what takes how many operations exactly. In fact, it might be different in different implementations of Python, different computers. The C here refers to all the things that are outside the loop. So we only return I once, that's technically inside the loop, but we just do it the once. We only set up range the once, we only look up length of L the once, stuff like that. So the takeaway here is, in the worst case, if E is at the end of L, the runtime will be proportional to length of L. Why is that? Well, because this is how many operations approximately we are taking. And then this is some kind of number. It doesn't even matter what number it is, because it's going to be correspond to different amounts of seconds on different computers. And then this is what's actually important here, is it's length of L times something plus something else. So the something else doesn't matter, because if length of L gets very large, then compared to that, C is going to be small, no matter what C is. This number doesn't really matter, because this is operations. What we care about at the end for any particular device is actually seconds. So we don't know how many seconds per operation. So if we assume that we take S seconds per operation, runtime is S times length of L times, so this I'll just take as 4 plus S times C. And the S we don't know. So the only thing we can take away from this analysis, again, this is the function, is the runtime in seconds is going to be proportional to length of L. Make sense? So to sum up, this is one way of approximating the efficiency of a function. So we call it the worst case symptotic runtime complexity. So this is a mouthful, but that's what it is. For an input of size n. This is for an input of size n for the input that makes us the most unlucky. What is the runtime proportional to? The answer in this case, based on this analysis, is so for length of val equals n, the worst case runtime is proportional to n, approximately. Right? So worst case means that for any input of size n, if you choose the input that makes you the most unlucky, so that takes the most time, what is the runtime going to be? So in this case, it's important because in the best case, L is 0 is equal to E, and you return very fast. So we ask, what is it proportional to? Well, the reason we ask what is it proportional to, because if we don't have a specific device, that's the best thing that you can hope for, right? So because you don't know how many operations per second you take, you can have a formula that's like that, where you say, well, like that is the actual runtime, seconds per operation. So that is the actual runtime, but, well, depends on DS. It's going to be different, right? So what you can take away from this is length of val. The other thing, and we'll do it kind of more mathematically, maybe more mathematically than you want in a second. The other thing is, if you have this kind of thing, it doesn't matter. Intuitively, the reason it doesn't matter is that if length of val is very large, meaning for the cases where it's relevant, where the algorithm might take a long time, this term is going to be much larger than S times C. So it doesn't matter that you also add S times C. This term is much larger. Make sense? So that's the intuition. People sometimes get confused about worst case versus kind of the actual runtime. So worst case means for an input of a set length or a set size, a magnitude sometimes, what is the runtime if you get to choose the input that's as bad as possible, as long as it's of a fixed length. So if you plot it, where's my camera? So if you plot the thing like this, so because we said it's proportional to n, so it's going to look something like this. And you'll notice that here, that's valid regardless of what S is, regardless of what the conversion factor is between operations and seconds. And that's because, well, if S is large, I can just say, well, like a lot of seconds per operations, I'll just stretch it out. If S is small, I'll just compress it, but I didn't specify the scale here. So that's what it's going to look like. Now, it's not going to start at 0 exactly, right? And that's because we kind of said here, like for housekeeping, you needed to actually say, well, I need to copy the L first and I need to copy the E first. That's going to be the case regardless of the size of L. So here we're not exactly starting from 0. But if you focus out and look at the big picture, compared to how large this can be, this distance is going to be small. So it's approximately a line that starts at 0 for a large enough n. Usually, and sometimes in practice not, but usually we care about what happens for a large n, and that's just because if the n is small, you don't care, it's fast anyway. Okay. So this is that. So what I want to do now is, like for now, okay, like we have this. I want to give you a different algorithm for solving a similar kind of problem that's actually faster, just kind of to see the distinction. It's not always like that. Okay. And that algorithm is called binary search. So it turns out that if the list L is sorted, you can implement a much faster find I. So here's the idea. Let's say that L is like this. And E is whatever, 150. Let's say that L is sorted. So one option, if you're looking for 150, is to say, is this 150? Is this 150? Is this 150? Is this 150? Okay, finally found 150. That could take a very long time. But imagine how many have been to Roberts? You should visit sometime. It's great. So imagine you're looking for a book in the library. I don't know if anybody does it anymore, but imagine you are, right? And if you know, like how many people have been to a library recently? Not Roberts. Okay. So if you're looking for a book, right? Like you're not saying, okay, like that's not this one, that's not this one, that's not this one, that's not this one. You're actually kind of saying, okay, like if the index starts at Z, I'm going to look at the section of the library where the Zs are. If it starts with A, I'm going to look where the A's are. If it's in the middle, I'm just going to try in the middle. And that's exactly the kind of thing that you can do with a list, right? You could say, I know the list is sorted. So what I'll do is I'll just look at the middle of the list and say, well, is it on the right or is it on the left? And if 150 is on the right, as it is in this case, well, I just need to look here. If I'm looking for an element that's less than the middle, well, I just need to look here. Right? So for 150, it would be, well, like one of those is the middle. Let's say that this is the middle. Okay, that means that we just need to look at this part of the list. What do we do next? Well, look at the middle of this one. Oh, it's 150 already anyway. So 2 steps. Or if you're looking for E equals 1, then you could say, okay, it's smaller than the middle 50. Okay, so we are just looking here, smaller than 10. Okay, here it is again. Make sense? So that seems much faster. You don't have to look at every element. So let's try to actually write it down. It's not going to be super easy. So this is called binary search. So return the index of E in a sorted list L. So what I'm gonna do is I'm gonna keep track of the low and the high end of the list that I'm currently looking at. So initially I just say, okay, so low is 0 and high is length of L minus 1. And I such that L at I is equal to E is between low and high. And what I'm going to keep doing is this exact idea, right? So I look at the middle and I say, okay, do I just look on the left or do I just look on the right? The way I write down what I'm currently looking at is I update the low and the high. So I'll leave this empty for now. And I'll say, okay, look in the middle. So the middle is going to be just the average between low and high. And now we have three situations. So one situation is we found it anyway. Right? So if L at mid is equal to E, you don't need to know anything else. You found the answer, just return mid, you're done. So if L at mid is smaller than E, what does it mean? So let's say that mid is over here. And you're saying L at mid, so this guy is smaller than the element you're looking for. So that means that the answer must be to the right. Make sense? So, okay, if the answer must be to the right, then it must be that low is now mid plus 1. And high is what it used to be, right? So if we start out with low being 0 and high being 0, 1, 2, 3, 4, 5, then now we'll just say, okay, we compared mid to the element we're looking for, and it's smaller. So high remains the same, and low is now over here, the element to the right of mid. If it's not equal and it's not smaller, it must be larger, so it's the other way. So it's the situation where E is something like 1, and you're comparing it to mid and it's smaller. So that means that the answer is somewhere in here. So that means that low stays the same. So it used to be that it was the entire list and 200 was the high. And now we want the location of the 50 to be the high. So we'll say high is equal to mid minus 1. Okay. So, and we're going to keep repeating it. So we're going to keep updating low and high until we zeroed in on the actual answer. So when have we zeroed in on the actual answer? Well, so what I'll do, just because it's going to work out in the case that E is also not an L, is I'll say if high minus low is greater than 1, then I'll keep going. If high and low are within 1 or 0 of each other, then I stop. So if I stopped and did not return, so at this point, high minus low is either 1 or 0. And what I can do is I can say, okay, at this point, either there is no answer, or the answer is low, or the answer is high. I'll just check. So if L at low is equal to E, return low. And if L at high is equal to E, return high. And if neither of them are equal to E, well, that means that the element is not actually in the list. So I'll say return none. And here I can remove this condition and say something like this. So the reason I did it like this, there is not a way that I'm aware of to explain why this is like the most elegant solution. It's one of the possible solutions. You can see that it's kind of awkward, like you'd like just to say, while high minus low is not equal to 0, but that wouldn't work because sometimes that results in an infinite loop for annoying reasons. So that's like one of the ways to get out of it, is such as say stop when high minus low is equal to 1, or if it's equal to 0, then it's fine as well. And then just manually check down below, is L at low equal to E, is L at high equal to E. Be done with it. That's kind of as elegant as it gets, in my opinion. There's different aesthetic judgments there, but like there is not like a straightforward way to make it like nicer than this. And this is like not too bad. Okay, so let's go back. Let's do kind of a slightly larger example just to give people a sense of how this would work. So let's say that we're looking for E equals to 10. Well, 10 is boring. E equals to 500. So what happens? So initially low is equal to 0, and initially high is equal to length of L minus 1. So 0, 1, 2, 3, 4, 5, 6, 7. So that means that the first mid is 0 plus 7 over 2. So that is 3. And we're saying, is L at 3 smaller or larger or equal to 500? The answer is smaller. So that means that we want to focus on this part of the list. So that means that we want low to be the index of 150. So 0, 1, 2, 3, 4. 3 plus 1. So now low is 4 and high is 7. So this is the part of the list that we're focusing on. And next time mid is going to be in the between 4 and 7. So 4 plus 7 over 2 would be 5. 0, 1, 2, 3, 4, 5. So we are here. And we're asking, is this smaller or larger than 500? The answer is smaller. So that means that low becomes 6. Once low becomes 6, it's not the case that high minus low is greater than 1. So we just go down here and we check and we get the answer. Make sense? Questions about this? Let's see what Discord is saying. Discord is very quiet today. Okay. So we have 5 minutes. So I'll give you the preview of the analysis of why this is much faster. So like the intuitive reason that this is faster is you don't have to look at every element now, right? So you get to skip stuff. So this is clearly faster. But this doesn't give you a sense of how much faster it is. So here's one way to think about it. And like people talk about it. I don't know if it's like a diversion or not. So there is this game that people used to play in cars before they had phones. Maybe people still play it. So it's called 20 questions. So the idea is like this. I think of a secret object or person or something like that. And you get to ask me yes or no questions. And I answer yes or no. And then if you figure out what I'm thinking of or who I'm thinking of in less than 20 questions, you win. Otherwise, I win. Okay. So the way it might go is you might say, well, like, is it a person? And I would say yes. And you would say, are there a student? And I would say no. And you would say, are there a politician? And I would say no. You would say, are there a professor? And I would say yes. Do they like rigorous thinking? And I would say yeah, and so on. Okay, so something like that. So the reason I bring this up is it's kind of related to figuring out the location of an element in the list. You're saying, is it in the first half or is it in the second half? Is it in the first quarter or in the second quarter? Is it in the third eighth or the fourth eighth? And so on. So it's the same structure. So going back to 20 questions, the fact that this game is kind of feasible, that you can sometimes win and sometimes lose, indicates something about the number of concepts that you can have. And the reason is this. Imagine that you are asking the most efficient questions possible. How would it go? So we start with n possible concepts. So if you ask the most efficient yes/no question, leaves you with n over 2 possibilities. Right? Because if you ask a question like, is it will exclude? Well, that's not an efficient question because if I answer no, well, you excluded one person, but there's like everyone else. Right? So the most efficient thing is to say, like, how do I split up the space of concepts in half and leave just half of leave half either way? In the same way, like in Wordle, like if you play Wordle, that's like you want to make a guess such that you exclude the most possible number of possibilities. So, okay. So that's like this. And then the next question should leave you with n over 4 possibilities. And so on. So what's the pattern here? So the pattern is you start with n, and then you have n over 2, and then you have n over 4. And then by the end of the 20 questions, you are left with n over 2 to the 20 possibilities. 19. Because you start with actually, sorry. So you start with this, and then the last one, you get to ask one question. So here, like this is after the first question, after the second question, after the 19th question, after the 20th question. So if it's possible to ask questions efficiently, that means that in 20 questions, you can be left with just one possibility. So that implies that there are about 2 to the 20 concepts at most that are possible. In fact, it's less. Right? So what does this have to do with this? Well, just to give you a preview, I'm asking one question, leave out half the possibilities. Ask another question, leave out 3/4 of the possibilities. Ask another question, leave out 7/8 of the possibilities, and so on. So how many questions do I need to ask? Well, log 2n. If you don't know about logs, there's going to be a preview on Wednesday, at which time I'll see you. Bye. Thanks. Yeah, so the project, by the way, is set up on Gradescope, so feel free to submit. There's not going to be any tests that were not given out initially. You have to think of them yourself.